let's talk about the arc-length function, which is a little bit different than what we had talked about before. Okay, I want you to imagine that we have some pre-established path, like this curve y is equal to f of x. So you can think of this as a pre-established path. And our starting point is going to be x equal to a. Okay, and then what this arc-length function is going to do is it's going to take its input value as some point x. So let's say that I put my x to be right here. Then what's going to happen is we're going to calculate the arc length from A all the way to whatever the input value x was. So the output of the function will be this length starting at A going to x. All right. If we move x a little bit further down, so let me say that this is x1. Let's say you moved it down over here to x2, then the output of s of x2 would be the arc length starting at A going all the way to x2. Okay, so you could almost think of this arc length function as sort of acting like an odometer in a car that tells you how far you've driven. So it's like this blue line is the path or the road that we're driving along, and when you input the x, it'll tell you the length that you've driven. All right, so what is this arc length function? Well, it's going to look very similar to the arc length that we calculated before. So let me show you. We're going to calculate the integral. We're going to have the square root of 1 plus f prime, and I'm going to call my integration variable t instead of x, and I'm going to square it. So that's the integrand. Our variable of integration is going to be t, so let me write dt at the end there. The starting point for our integral is going to be the starting point a, but because the end point is going to be moving and depend on this independent variable x, I should put an x for my upper limit of integration. I'm going to highlight this upper limit of integration x just to make sure we all realize that that's changing, that's the independent variable of our arc length function. All right. All right. So another big thing that we care about is we care about this idea of ds. Now, what is ds? ds can be thought of as a little bit of arc length. Arc length. Maybe I should put that in quotes. Okay. So what do I mean by that? Well, what we can do is we can take the derivative of this function right here, this arc length function. And when we take the derivative of this arc length function with respect to x, we're going to get ds dx. And when we take the derivative of this integral, we know that derivatives and integrals are inverse processes. So according to the fundamental theorem of calculus, part 1, this ds dx is going to just be equal to the integrand square root of 1 plus f prime. And then what we do is we have to replace the t with an x. So the derivative of that integral function is simply the integrand, and we replace the x. So this is really from the fundamental theorem of calculus, part 1. So we have learned this in first semester calculus. We usually use part 2 all the time to calculate definite integrals, but in this case, we want to use part 1. And the next thing I want to do is I want to regard this ds dx. Think of this as a ratio or a quotient of two differentials. So I can solve for ds by multiplying both sides by dx. I get ds is equal to the square root of 1 plus f prime of x quantity squared dx, like this. Okay. Now, I can rewrite this as well using Leibniz notation. So I could also write this as like, or this ds is equal to the square root of 1 plus dy dx squared dx. Okay. The great thing about this is that if I wanted to describe my function with not as with x as the independent variable, but if I wanted to use y as an independent variable, in other words, we're pretending that we have some function that looks like x is equal to g of y, then we can write ds dy as the square root of 1 plus g prime of y quantity squared. Solving for ds, we get the square root of 1 plus g prime of y quantity squared dy, or ds equal to the square root of 1 plus dx dy quantity squared times dy. All right, so I am going to highlight these ds formulas because we actually need to use these when we talk about surface area in the next section. And understanding surface area is going to be far easier if you can train yourself to think about things in terms of a little bit of arc length. So that's what really these two DS's are talking about. DS is a little bit of arc length. All right, everybody, this concludes our video on the arc length function and DS. Take care.